QC Ware is a Palo Alto-based quantum computing software company that provides cloud access to nascent quantum computing hardware systems. The QC Ware platform allows enterprise users with no presumed prior knowledge of quantum computing to exploit several different quantum computing hardware platforms for various tasks through the use of application programming interfaces made available in Python. As of July 2018, the QC Ware platform includes support for the Cirq quantum computer interface and simulator developed by Google. QC Ware currently makes available the Cirq simulator as a backend, and the Cirq interface will ultimately act as a gateway to Google's quantum computing hardware. QC Ware has already completed integration of the Cirq simulator as a backend for our optimization API, and we expect to release more Cirq-powered API calls in the future. I'll show a quick demo of solving the max-cut optimization problem using QC Ware's Cirq implementation of a quantum optimization algorithm, QAOA. First, an introduction to the unweighted max-cut problem. The objective of the max-cut problem is to bipartition the vertices of a graph such that the number of edges connecting the two sets is maximized. Slightly less formally, we wish to maximize the number of edges cut by the boundary between the two sets of the partition. As you can see in this graph, the maximum cut partitions the vertices of the graph into two sets so that we have as many edges as possible that begin in one set and end in another. Max-cut is an NP-hard problem, which implies that there are no known polynomial time algorithms that solve it optimally in less than exponential time. Given its difficulty, it is a natural candidate for targeting with quantum optimization algorithms like QAOA. Solving max-cut using the QC Ware platform is simple. As you can see, it takes only a few lines of code. We import the QC Ware Python library, which allows easy access to the QC Ware platform. This library can be installed on your own system using the simple command pip install QCWare. For this demo, we are going to solve max-cut on a complete graph with 4 vertices, but we are not restricted in general to particular graph types. This code simply displays an illustration of the graph at the end, showing us that the QC Ware platform is indeed finding a valid solution via QAOA running on the Cirq simulator. These 2 lines convert the adjacency matrix of the graph to a quantum unconstrained binary optimization, or QUBO, problem. This is the format in which we will send the problem to the QC Ware platform in the cloud. In the QC Ware platform, changing between the hardware or software simulator is as simple as changing one line of code. For this demo, we're choosing the Cirq QAOA solver running on the Cirq quantum simulator. This one line here is where the good stuff happens. The solve binary function exposed by the QC Ware platform optimization API. Given a user access key, the problem to be solved, the choice of solver, and any additional required arguments, the solve binary function returns the best found solution. Finally, we draw a figure of our results. In just a handful of lines, we have managed to write code that will approximately solve a binary optimization problem. Let's run it and see that it works. We see here that the program begins by defining an arbitrary graph and then running the optimization routine. And now it's found a solution, a bipartition of the graph that maximizes the number of edges between the two sets of the partition. These red nodes are in one set and the blue nodes are in the other. The boundary between the two sets is here, and informally you can see that this boundary is the one that results in the most number of edges crossing it. The max-cut problem is just one of many possible optimization problems that can be run via the QC Ware platform. As you have seen, the QC Ware optimization API provides an easy-to-use, high-level interface for allowing users to solve problems using quantum algorithms, with the details of how the quantum algorithms themselves work abstracted away. One optimization problem of potential commercial interest is the combinatorial auction problem. In a traditional auction, each item is presented for bidding one at a time. Maximizing profit is simply a matter of choosing the highest bid for each item, which is computationally trivial. In a combinatorial auction, potential buyers can submit bids for any number of the items with one price offering for a set of items. Since each item can only be sold once, this becomes more difficult and is in fact NP-hard. This combinatorial auction situation can be found in the real world in ad sales, RF spectrum auctions, and other business sectors. Here we see an implementation of a randomly generated instance of the combinatorial auction problem. Each bid specifies a group of items that the bidder wants to purchase, as well as a price for the package. The output of the program here shows the optimal set of bids to accept, with a bit string with 1 bit per bid. A 1 indicates that we should accept the bid, and a 0 indicates that we should reject it. Here we see that the solution is to accept the second and fifth bids, which maximizes our revenue. Enterprise users can solve this real-world problem in a similar fashion to the max cut problem from earlier. First, we encode the bids into a QBO problem, and then call the solve binary function from the QC Ware library, which uses the Cirq QAOA implementation to find a solution. Please contact info@qcware.com for more information or to get access to the QC Ware platform.